In a previous video, we looked at exponential functions and then eventually exponential equations. And I talked about how we might need a better way of trying to solve exponential equations because all we had for certain types would be kind of guess and check. Well, this way is going to be called the logarithm, and we'll go into a little bit depth as we keep going down the page. But basically, a logarithm is an inverse of an exponential function, and it's that by definition. So it's not something we develop, it's something we define. So we'll go ahead with the definition here. We see two different statements here, and we see this arrow going both ways. So basically they're definitions of each other. So let's start over here on the right with something we know. B raised to the C equals A. So we write this in generic terms, so think about position and try not to think about any assignment we ever made to these letters. B here is a base to an exponential, where C is the actual exponent. So this could be something like 2 to the 5th or something like that, equals A. So that would be the result. What we want to do is we want to hold these positions of B, C, and A, and we're going to write it in something called a logarithm, and whatever the values of B, C, and A are, we will just kind of fill them in on this side. So the correct terminology here, as we said, C would be an exponent and B would be a base. And we call the A the argument, which is the argument of the logarithm. So let's see if we can use that to rewrite a couple of things. So here's our first example, and I guess it's the one I was thinking about when I mentioned that. But it says we're going to try and rewrite 2 to the 5th equals 32 as a logarithm. So we kind of want to follow this model up here that we had, and we have basically B being 2, C being 5, and A being 32. So if we take that value for A, B, and C and place it over here, we should get, I believe, the first one, which would be log base 2 of 32 equals 5. Whenever you write a logarithm, the base from the exponent is always the subscript, and the exponent always ends up on the side by itself. Okay? So if you can use this simple conversion up here, definition of a logarithm, then you'll be able to rewrite any logarithm you like. But keep in mind that A, B, and C here are placeholders, so they don't necessarily have to be a number. They could be an expression. They could be something a lot more complicated. They could have their own variables in place of them. So let's see another example here. So here we start with the logarithmic form. Log base 4 of 16 equals 2, and we're going to write it as an exponential. So here we see B being 4, A being 16, and C being 2. So if we switch all that around, we'd have 4 squared equals 16. And these numbers should make sense right now, but if you had a variable in there, it wouldn't necessarily be something you could put in your calculator and verify. So let's look at something possibly a little bit more complicated, and that's actually solving an equation. So here we have an a logarithmic equation where we want to solve for x. Log base 3 of 27 equals x. So we don't have much work or much background in this log definition up until this point. So what we want to do is we want to take it to something a little bit more familiar, if we don't have a way to put this in the calculator yet. And we could rewrite it as 3 to the x equals 27. Now, depending on how familiar you are with this, you may realize that 27 can be written as 3 cubed. And if that's the case, you could rewrite that as this is 3 to the x equals 3 cubed. If you compared both sides, then 3 equals 3. So the exponent x equals 3, so 3 must be the answer. In the future, you'll get a way to put this in your calculator and understand a little bit better, or at least get them easier. But here we did change this thing into an exponential equation, so keep in mind that we may have some rules of exponents that could be useful from our first lesson in this course, which was back in chapter 1. Okay, another logarithmic equation here. So we'll solve for x again. We got log base 5 of 1/25 equals x. These we can do in our head, or at least on paper using some of our rules, because we know 25 is, I'm going to mistype this. I need to go back and change that. Okay, I apologize. I paused that, and magically that 25 under there has changed to 125. Okay, and if you're familiar, you may understand that 125 is 5 cubed. Well, if we write it that way, we got 5 raised to the x equals 1 over 5 cubed, which doesn't really let us compare 5 to 5 since 1 is in the numerator and 1 is in the denominator. So we can use one of those negative exponents to bring that 5 cubed in the bottom up, and it would be 5 to the negative 3. So we've got 5 to the x equals 5 to the negative 3, which means the same basis here, so the exponents must be the same. X equals negative 3. So basically we rewrote this equation as an exponential equation. Okay. And then we tried to do some magic with our rules of exponents so that we could get the same base on each side, so we could just compare exponents. Now, that's not always going to be an option, but it does give you an understanding of how things are working right now and how logs are defined. So this x up here should be negative 3 for that to be a true statement. Now let's talk a little bit more about how logarithms and exponentials are inverses of each other. So you may remember from talking about inverses that an inverse undoes what the original function does. So square root is the inverse of x squared, and vice versa. There might need to be some concessions made to the domain there. But here I've got two functions. The first one is 2 to the x, and I've put here a little table of inputs, outputs, or x and y's. Plug in 0, 2 to the 0 is 1. Plug in 3, 2 cubed is 8. And the logarithm, we'd have to go back through the things that we just did, but if we were to plug a value in for x here, we could say log base 2 of 1. We'd have to change that to 2 to the unknown equals 1, so it'd have to be 0. We could plug in 8 if we tried that and reworked it like we did in the previous examples, change it to an exponential, we'd get 2 to the third equals 8. And what we can see here are these tables are kind of mirror images of each other. This one the x is 0 and the y is 1, whereas this one the x is 1, the y is 0, so it takes it back to where it started. I also want to show you graphically here. The left is 2 to the x, where the right is log base 2 of x, and these are the set of points that are in that table up there. But what you'll see is they're kind of mirror images of each other. If we were to draw a line at y equals x, just a straight diagonal coming across here, we could flip this graph around, and each one of these points switches the x and the y. So like we said, this one here was 0, 1. This one here is 1, 0. This one right here is 3, 8. The black one over here, the black one is 8, 3. So they've been switched around. So keeping in mind that inverses switch the x and the y, or switch the input-output values. I think that is it. Yes. Thank you.